Hello students, in this class let us study how power factor is improved by using capacitor. We know that power factor is the cosine of angle between voltage and current. Most of the loads in power system are inductive loads. So in an inductive load we know that current lags voltage by an angle phi. So this is the phasor diagram showing an inductive load. So here V is taken as the reference and current I lags behind voltage by an angle phi. Current I is resolved into two components, one along voltage V and another 90-degree out of phase with V. So the component that is along voltage V is I cos phi. I cos phi is called as active or wattful component, and the component which is out of phase 90-degree out of phase with voltage V is called as I sin phi, which is called as reactive or wattless component. In order to improve the power factor, we have to reduce the reactive or wattless component I sin phi. If the reactive component I sin phi is small, then angle phi will get reduced so that we can improve power factor. So for smaller reactive component, higher will be the power factor. Now let us consider the power triangle. Power triangle is obtained from this phasor diagram. Multiply each with voltage V. Then we will get power triangle. So this is the power triangle. OA is VI cos phi, which represents the active power in watts or kilowatt. AB represents reactive power, which is VI sin phi in volt ampere reactive or kVAR, and OB represents apparent power. VI apparent power is VI, which is expressed in volt ampere or kilovolt ampere. So from this triangle we will get OB square is equal to OA square plus AB square. That is apparent power square is equal to active power square plus reactive power square, and take cos phi from this power triangle, then we will get power factor cos phi is equal to active power by apparent power, that is kW by kVA. So as I said earlier, we have to reduce this reactive component so as to obtain higher power factor. Let's see what are the disadvantages of low power factor. For single phase supply, power P is equal to VLIL cos phi. From this we will get IL as P divided by VL cos phi. For three-phase supply, P is equal to root 3 VL IL cos phi. So IL is equal to P divided by root 3 VL cos phi. Let us consider that power and voltage are fixed values. Then IL is inversely proportional to cos phi. So as cos phi decreases, IL, load current IL, increases. So we have to improve cos phi in order to reduce this load current. Let's see what are the disadvantages. First one is large kVA rating. We know that cos phi is equal to active power by apparent power. So apparent power is equal to active power by cos phi. That is power factor is equal to active power in kW divided by apparent power in kVA. So from this equation, kVA is equal to active power kW divided by cos phi. Most of the electrical machineries are expressed in kVA. So kVA is inversely proportional to cos phi. So if cos phi is less, or when cos phi decreases, kVA has to be increased. So at lower power factor, the kVA rating of the equipment has to be made more, making the equipment larger and expensive. The second disadvantage is greater conductor size. So from this equation, we understand that as cos phi decreases, IL increases. So in order to transmit this large amount of current, the conductor size should be greater. So to transmit or distribute a fixed amount of power at constant voltage, the conductor will have to carry more current at low power factor. And also this more current will lead to large copper losses. We know that copper loss is equal to I square R. So as current increases, I square R losses also increases. This results in poor efficiency. And also this will also lead to poor voltage regulation. There will be greater voltage drops in equipments as well as transmission lines. So these are the disadvantages of low power factor. So in order to eliminate these problems, we have to improve the power factor, or we have to maintain power factor closer to unity. And the last one is reduced handling capacity. That is, we cannot operate the equipments in its installed capacity. So this the lagging power factor reduces the handling capacity. So let us study how this power factor is improved by using capacitor. First, consider an inductive load which takes the current I and voltage V is across this inductive load. Now first consider the phasor diagram of this inductive load. We know that in the case of an inductive load, current lags behind voltage by an angle phi. In this case, let us take that angle as phi 1. So this is current and this is voltage. We have to improve power factor. That is, for lower angle we will get higher cos phi. So we have to reduce this phi 1 to lower value, then cos phi will get improved. For that, connect capacitor in parallel with this inductive load. We know that capacitor draws reactive power. So this inductive lagging reactive power can be compensated or can be decreased by using this leading kVAR produced by or given by capacitor. Consider the phasor diagram of this second circuit. So first take voltage as reference phasor, and initially the current was I. So current lags voltage by an angle phi 1. Now in the second circuit, a capacitor C is connected in parallel with the inductive load to improve the power factor. In case of a pure capacitor, current IC leads voltage by angle 90 degree. Okay, so from this second figure we know that I dash, the net current I dash, is a phasor sum of capacitor current IC and the load current I. So we have to draw this net current in this phasor diagram. How will we draw this? First, draw V as reference phasor, then draw current I at an angle phi 1. Next, draw IC at an angle 90 degree with V. We know that IC leads voltage by 90 degree as this is pure capacitor. Then I dash is the phasor sum of IC and I. So draw I dash as the phasor sum of IC and I. We know that I dash and I dash makes an angle phi 2 with voltage V. From this phasor diagram, it is clear that the initial phi 1 got reduced to phi 2. Thus, power factor is improved. So here, phi 2 is lesser than phi 1. That means cos phi 2 is greater than cos phi 1. Thus, power factor is improved. Now, let us study some equations obtained from that phasor diagram. So, from this phasor diagram, it is clear that the current I dash, that is the net current I dash is lesser than I. From this phasor diagram, it is clear I dash is lesser than I. The second point is resolve this I dash and I into two components, one along V and other 90 degree out of phase with V. When we resolve I dash along V, we will get I dash cos phi 1, that is this point. Then when we resolve I along V, we will get, here it is I dash cos phi 2. We will get as I cos phi 1. That is I dash cos phi 2 is equal to I cos phi 1. Both are equal. That is, we can understand from this phasor diagram. So, there is no change in active power by improving power factor. The only change is in reactive power. So, I dash cos phi 2 is equal to I cos phi 1. Next, let us resolve I dash and I 90 degree out of phase with V. So, this will be 90 degree out of phase with V. So, this will be the point I dash sine phi 2. And this will be the point I sine phi 1. So, I dash sine phi 2 is the net current. So, from this phasor diagram, it is clear that I dash sine phi 2 is lesser than I sine phi 1. That is, I sine phi 1 was the initial reactive current. It is reduced by IC and we will obtain I dash sine phi 2. So, from phasor, we can write it as I dash sine phi 2 is equal to I sine phi 1 minus IC. That is, by using capacitor, I sine phi 1 is reduced. That is, IC neutralizes I sine phi 1. Thus, the power factor is improved. So, we can say that I dash sine phi 2 is equal to I sine phi 1 minus IC. Now, multiply this first equation and second equation with V. So, the first equation becomes Vi cos phi 1 is equal to Vi dash cos phi 2. That is, there is no change in active power by using a capacitor. Now, multiply the second equation with V. Then we will get as Vi dash sine phi 2 is equal to Vi sine phi 1 minus Vic. That is, this equation is multiplied by V. That is, from this equation, we can understand that net kVAR after power factor correction is equal to lagging kVAR before power factor correction minus leading kVAR of equipment. That is, net kVAR is Vi dash sine phi 2. is equal to lagging kVAR before power factor correction. The initial kVAR was VI sin phi 1. It is reduced by the kVAR given by the capacitor. So VI dash sin phi 2 is equal to VI sin phi 1 minus VIIC. So the reactive power is decreased, thus power factor is improved. This was the phasor diagram of a single phase. Now if we use a three-phase load, we have to connect capacitor in each phase. So this capacitor can either be connected in star or delta, and this capacitor is generally known as static capacitor. Static capacitor is same as this is also a static capacitor. We commonly call this capacitor as static capacitor. Now let us see the advantages and disadvantages of static capacitor. The advantages are they have low losses, they require little maintenance as there are no rotating parts, they can be easily installed as they are light and require no foundation, and they can work under ordinary atmospheric conditions. The disadvantages are they have short service life ranging from 8 to 10 years, they are easily damaged if the voltage exceeds the rated value, and once the capacitors are damaged, their repair is uneconomical. So these are the advantages and disadvantages of static capacitor. So this is all about power factor improvement by using capacitor. Now let us do some previous year university questions. A power station has a maximum demand of 15,000 kW. The annual load factor is 50% and capacity factor is 40%. Determine the reserve capacity of the plant. So the given values are maximum demand of the power station, which is 15,000 kilowatt, annual load factor is 50%, and plant capacity factor or capacity factor is 40%. We have to determine the reserve capacity of the plant. To find out the reserve capacity, we have to first find out plant capacity, because reserve capacity is equal to plant capacity minus maximum demand. So first we have to find out plant capacity. So here plant capacity factor is given, which is 40%. So here average demand is not given, so in place of average demand substitute units generated per annum divided by hours in a year. Here annual load factor is given. So first we have to find out units generated per annum. So here load factor is given. We know that load factor is equal to average load or average demand by maximum demand. From that equation find out energy generated per annum or units generated per annum. And here average load is not given, so in place of average load substitute units generated per annum by hours in a year. Then we will get energy generated per annum. Plant capacity as 18,750 kilowatt, and the reserve capacity is plant capacity minus maximum demand. Plant capacity is 18,750, maximum demand is given as 15,000. So when we subtract both, we will get the answer as 3,750 kilowatt. Now second problem, this is also a previous university question. Power factor of a three-phase load of 25 kilowatt at 415 volt 50 hertz is to be improved from 0.6 to 0.9. Calculate the value of the capacitance required in each branch if the capacitor bank is in delta configuration. So the power factor is to be improved from 0.6 to 0.9. The load, the active power of the load is given, which is 25 kilowatt, and this is a three-phase load. So in each phase capacitor is connected in delta configuration. We have to find out the rating of capacitor connected in each phase. So for that, first original power factor is given, which is take it as cos phi 1. Cos phi 1 is equal to 0.6. Cos phi 2 is equal to 0.9. So from this find out phi 1 and phi 2. We know that phi 1 will be equal to cos inverse 0.6 and phi 2 will be equal to cos inverse 0.9. From that we will get phi 1 and phi 2. Then find out tan phi 1 and tan phi 2. Because we have to obtain the leading kVAR given to the capacitor bank. So leading kVAR taken by the capacitor bank is P, active power P into tan phi 1 minus tan phi 2. So active power is given as 25 kilowatt. Tan phi 1, we calculated tan phi 1 and tan phi 2, substitute these values, then we will get leading kVAR taken by the condenser bank. Condenser bank is same as capacitor bank. Now the question is to find out the capacitance required in each branch. So rating of capacitor connected in each phase is 21.15 divided by 3. Try to do this problem as homework. This is similar to the last problem. Try to do this. Okay. Thank you.